Thank you so much. So here I am. I'm going to give you a little bit of a scoop on my version of what 5G is going to be doing and what we're going to see ahead of us. So just to give you an idea where I come from, this is sort of the team of companies that support me and activities that we've been doing. And a lot of my PhD students actually in Dresden want to stay there. And so since there's no local business, we just start companies. So here are 16 companies started so far. Some of them have seen an exit already. And so if you talk about 4G, 3G, whatever all, and Wi-Fi, there are plenty of companies here in this area. So think of me not only being an academic, but also a little bit of an entrepreneur. Now, to get into the 5G, I think it's important to take one step back and have a look at what we had in history on the wireless roadmap. And if we look at history, obviously it's nice to look at these two pictures. This is the photo, obviously, of the election of the Pope, in this case, Pope Benedict. Everybody's waiting on Via della Conciliazione to see what happens. And a couple years later, Pope Francis was elected, and this was what happened there. Now, the interesting part is here are two people, one here and one there, that are actually communicating. And these people are not communicating, they're just taping. If they were to communicate this and pipe this into the network, we need terabits per second. So if you think that 100 megabit is enough or a gig is enough, forget it. We need more data rate. So I came up with this wireless roadmap when our first startup, Systemonic, was bought by Philips Semiconductor, NXP, and I was chief scientist and had to meet the CTO, and I told him, I think you have to invest in cellular and in Wi-Fi because there is a continuous race going on, and he didn't believe it. And I sketched these lines, and I said, in 2015, we're going to have 100 megabit per second in cellular, and everybody said, that guy stayed in Berkeley for too long and inhaled too much. Anyhow, so what you see this here is now, today, 100 megs is not what we want. We want more than that. And obviously, if we talk about a terabit Wi-Fi system, that's only, what is it now? 8 years ahead from us. And we will have something even up to a terabit in cellular. So the question is not, will this happen? The question is how to do this. And this is a total fun part of research, of how to do research and actually look at this and drive this wireless roadmap forward. So this has been the content of 2G, 3G, 4G. You see 2G, 3G, 4G. And now 5G is going to come up. And 5G is addressing this also, like if 5G phase 1 with a new radio, we're going to see this happening. But 5G is more than that. And let's think of two new aspects, two new doors that are being opened, actually, if you think of 5G. One of them I like calling the thing book. We are human beings, and as human beings, we try to collect and hunt different things. So we want to monitor and sense all kinds of things, yes? So we have all kinds of sensors everywhere on planet Earth that we would like to have. And if we were able to have a sensor connect directly to the cellular network with a AAA battery and running for 10 years and continuously giving us some information, this would be great. Then we would buy this if it costs like $1 a year. Now that's maybe a market that is big, maybe 10 billion units a year, but not that big. Why? Because comparing this to what can happen, if we put this sensor into the cellular concept, this means we have a back channel. We don't only collect, but we can switch. We can turn things on and off. We can have every light bulb having a narrowband IoT sensor in there. And with that, basically turn on and off light bulbs, have things turned on and off. You can even, if you lost your phone and you want to know where it is, you just turn it on because it has an additional narrowband IoT sensor. And then if we add positioning to it, as is being done in the narrowband IoT standards coming in June, we can track and tag all kinds of devices. And this is a gigantic market. Just think of it. FedEx, UPS, DHL, and all these companies send out 500 billion envelopes and packets a year. So this is about 1 trillion units a year that you can sort of start selling. This is huge. So this is the market of narrowband IoT. And this is something we don't know of today. And this has a ton of challenges ahead. If I am selling 1 trillion units a year, some of them, like on a FedEx envelope, are only active for 2 weeks. until they reach the destination. Others are active much longer. How do I manage these things? I have to be able to build a whole infrastructure in managing these devices, because just think of it. If you sold this service as an operator and it costs $1 a year, and suddenly you find out, oops, something went wrong and somebody's calling 1-800-HELP-ME, the business proposition is gone. So you need to be able to build a whole infrastructure, not only in terms of chips, but also service, monitoring, operations of this kind of system. And finally, we're seeing the game of the millisecond coming. So the tactile internet, as we name it. What is that? So 7 years ago, when I was on sabbatical in Berkeley, I was thinking, looking at my cell phone and thinking, so bigger screen, nicer screen, more pixels, what else? And as I was moving it, I thought, actually, I'm moving it, I'm seeing some visual interaction. I'm moving it, I'm controlling it. So if we touch and move an object in front of our eyes, what is the reaction time our visual system, our eyes, want to see this so that it seems real? So if we do this remotely and we move this, we can see a lag time, or we cannot see a lag time. If it's real time, we don't see a lag time. It turns out the lag time that is allowable is in the range of 1 millisecond. If we're really moving an object in 3D, it's 1 millisecond. If we're moving a mouse over our screen, it is 10 milliseconds. So it's somewhere in the 1 to 10 millisecond. It's not. And depending upon what the human being's visual skills are, it's different. Anyhow, so it sure is by far a big step forward from what we have today in terms of LTE with 50 millisecond round time. Who knows that the millisecond counts? The gamers. Why? Because the speed of light is really slow, because light only travels at 300 kilometers per millisecond, which means if you want to do internet gaming, real time over the Atlantic or over the Pacific, there's no chance because the speed of light is too slow. You're going to get way more than 10 milliseconds. And if we go to a fiber optic cable, it's even slower. It's only 200 kilometers per millisecond, so a little more than 120 miles per millisecond. That's not much. Now, what is it, however, that we also know from gaming? That is, if we put VR goggles on and move our head back and forth, we can get sick to our stomach. Why? Because it doesn't react in the millisecond. So we really need to make sure that these VR goggles are pretty good and are understood. Otherwise, our poor leaders of the nations will start getting oozy, and we don't want that to happen. So what we said is, so here's a friend of mine, Frank Fitzek, colleague of mine in Dresden, and we sat down and said, let's try to see if this millisecond really makes sense. Everybody talks about it. No, nobody talks about it at that time. Today, everybody talks about it, but at that time, nobody talks about it, and so we said, let's build an experiment. So we say, take an Oculus, put 2 cameras on top, and so now we can set the delay time of what you see and what you get into a different mode. And you see here, this poor student is trying to catch the ball and is actually using his whole body. Now we crank up the latency to 150 to 200 milliseconds. And what you see is not very fair, because you see that this person is not really catching the ball. And why? Because if I throw an object, the speed of the object is about 1 centimeter per millisecond. And here you see at minimal lag time, the guy is catching the ball, but with about 10 centimeter displacement because of the 10 millisecond lag time. So it really is our natural human way of interacting with the network. And that is very interesting, because I think to make the network more human, it just has to be in the millisecond range. Obviously, that's the human side, which is interesting. So we can extend our skills. So some people talk about the Internet of Skills. We can do all kinds of things in terms of that. But it is not only about humans, the millisecond, it's also all over the place. It is if we start controlling robots. The robot actually should move at the speed of our motion, because if you move this robot with a remote control, it's really cumbersome. What we want to do is go in there with a humanoid robot and control it. We want to see what the robot sees with VR goggles. We want to control the object and actually run it as it sees. And finally, if we then go to the millisecond in factory automation, it's happening today already. It's there because these robots are actually controlled in the millisecond range. Why is that? They have about 1.50 meter dimension. So if two robots pick up jointly an object, they want to have a smooth motion and not jittering and jerking around and getting sort of Parkinson, right? Self-resonation system there. And to counter any self-resonance built up, you have to sample 10 times per period, and that's why in control everything is in the millisecond. So getting rid of the cables is big because that is one of the big expenses in running a factory, because these cables break and you always have to replace them. Getting power there is not the issue. But once you have a wirelessly connected robot, you can actually have a mobile whizzing on the factory ceiling and factory floor, picking up the pieces in time, on time, and actually do an in-time manufacturing of an individualized product. So what is the future of shopping? You go to a store, you don't see what you have on, you see something else. When you move, it should be reacting in a millisecond time frame, obviously the virtual mirror. Then you can feel different fabrics, you choose whatever you want, you push, I want this. We need a design assistant to help us, so very great job opportunity for artistically inclined people. Then it's manufactured individually in this individualized manufacturing plant, send off, and we get it back. And this is a complete new way of going to boutique stores and boutique design systems. Finally, I want to touch a little bit on the automotive side, just to give you an idea that the millisecond plays a role in automotive. Where could it play a role tomorrow already? That is, if you're the green car and you want to know if there's an orange car coming because you would like to pass the two slow cars in front of you. Obviously, what can we do? All cars these days more or less have cameras built inside, so we could actually connect these cameras, have a rendering system to give it a bird's eye view, render this together with the Apple Maps or Google Maps database, and then, based on that, actually calculate a bird's eye view in real time of what's happening and just put this in your heads-up display. And then as you're driving, you're seeing actually in real time if a kid is running into the street, if some object is in the way. Just think of this added level of security. Now, there is a millisecond in the cars today already, which you see in this experiment. Here are two completely identical cars. The left car has electronic stability control, the right one does not. Exact identical cars, different brands, but same car. This is by the German equivalent of the AAA, ADAC, a test done there. So what we see is to actually stabilize a car, we need this control loop between the wheels. Why is it 2 milliseconds? Because the wheels are about 3 meters apart, resonance frequency is 50 hertz, and as I said, 10 times sampling per period, so that gives us then the 2 millisecond reaction time. If we now go to the next level and want to build platoons of cars, we have to get this 2 millisecond reaction time into the platoons. So we have to connect the electronic stability control and the whole motion control, not only of one car, but of all cars. In a car-to-car scenario, this is an n-square problem of connectivity. Or we have an infrastructure that takes care of that. Once we have an infrastructure, we can do all kinds of crazy things. Anyhow, so Bosch gave us this thing that there is an issue coming up, and we didn't know this, so we set up this experiment here with Lego Mindstorms. Kids from 9th grade kids that spend 2 weeks at our labs in Dresden, at the 5G lab in Dresden, they put this together, and so they're tracking this black line, they're keeping a constant distance. What you don't see is that they're at the border of chaos. Because what happens is one car is actually accelerating, slowing down, accelerating, slowing down, and the second one, the third one as well, to keep a constant distance. If you have more than 3 cars doing this, you see this jerkiness, you see a chaotic system happening, and this is the reason why if cars on a freeway are too close to each other and the car in front of you is stopping while you are actually accelerating, you overreact, and if the car behind you is also starting to overreact, you get a spontaneous traffic jam. And obviously we want to get rid of these spontaneous traffic jams because we want to get rid of traffic lights altogether. We want to have cars whiz and crisscross over intersections. We want our personal bubble to be turned on so that we as a human just can cross the street and we are guaranteed nothing has happened. And obviously even the frog with a 5G modem is going to be a happy camper. So with this in mind, I can show you here a demo that we had last year at Mobile World Congress where we had this in action, and you see this car stops and everything is really nice with 2 base stations and the mobile edge cloud actually controlling these cars. This is the future. Now, if we look and take this one step further, obviously we take this into verticals, and this is the only vertical I want to touch and then finish, which is precision farming. In precision farming, what we want to do is we want to increase the productivity of farming on planet Earth by a factor 2 if possible, to really make sure that everybody is happy. So we need drones flying around to scan the field to make sure that no deer is hiding there and is going to be hopefully not chopped up by this machine. Everything is completely controlled because then you can compact the soil at the same pot where you compacted last year. You can increase the productivity of the other soil. And it's a big challenge, and we went out into the field, and here's some videos of our measurement on a tractor to see if this really can work and if we can actually have these latencies and delay times in the field to operate these kind of systems and these tractors at 2.5 centimeter at 1 inch precision. With this, I would say I gave you an idea of what this is about the tactile internet. It is a new era. If you think cordless telephony was it, when I lived in the States in the early 90s, everybody thought cordless is it, and that's about what we need. But cellular, actually making sure that we can initiate a call anywhere and reach anybody anywhere, and not only when they're close to a base station, is the killer app of wireless communication of cellular. So this is now happening, and we're taking it to the Internet of Things. With the tactile internet, we're going to do the exact same thing for remote controls. Today, a remote control is a point-to-point. Doing this via an infrastructure can make sure that drones, cars, whatever, fly along routes that are safe. And this is revolutionizing all these different industries. So we're at the doorstep of another 30 years ahead of us of revolution. With this, I would like to thank you for listening and I hope I gave you a little bit of an idea. So 5G is really exciting. It's about data rates, it's about massive Internet of Things, and it's about the tactile internet. And the 2 new game changers are massive IoT and tactile internet, building the infrastructure for remote controls. And with this, we have a happy 30 years ahead of us. Thank you.